This is one of those videos where I have to introduce a whole bunch of examples and ideas in order to motivate something, and you'll just have to trust for about 5 minutes or so that I do have a point that I'm getting to. As usual, pause if you need to process things. If I have two sets of things, there is a sense in which you can multiply those sets, by pairing up every element of the first set with every element of the second set in every way possible. This is called a Cartesian product. For example, the set of real numbers r consists of all numbers on the number line, and if I take the product of r with itself, denoted r cross r, I get the set of all pairs of real numbers. One way to visualize this is as a two-dimensional space, with the two numbers in each pair being the horizontal and vertical coordinates of a point in the space. Now, these are not just sets. There's some extra structure here. Both r and r cross r have addition and scaling operations on their elements, as follows. We can interpret an element of one of these sets as an arrow pointing from 0 to that element. The addition operation is given by stacking arrows tip to tail, while the scaling operation is given by lengthening or shortening arrows. This sort of structure is what we call a vector space. More specifically, a vector space is a set with two operations satisfying these axioms. If you're not familiar with this algebraic terminology, don't worry too much about it. I'm just putting these definitions here for completeness, so that interested viewers can pause and peruse. The important thing is that vector spaces are designed to mimic geometric space. And it turns out that if I have any two vector spaces, their product is also a vector space, where the addition and scaling operations are evaluated component-wise. This turns out to be a general fact about a lot of algebraic structures. Here's another example. A group is a set along with a single operation that has an identity and inverses. An example of this is the set of real numbers with the addition operation. The identity is 0 and the inverses are negatives. My claim is that if you take the product of two groups, you get another group. The real numbers with addition already demonstrates this, but let's find a more illustrative example. Let's say I have three things. A transformation which rearranges those three things is called a permutation, and I'm going to write permutations as a bunch of strings like this. The set of all permutations of three things is a group, where the operation takes two permutations and applies them one after the other to get a new permutation. Now, what's the Cartesian product of this group with itself? Well, it's the set of all rearrangements of 6 things, so that the first 3 stay on the left and the last 3 stay on the right. That is once again a group. Here's an example with a less algebraic flavor. A topological space is a set along with a chosen collection of subsets which we call open, and they have to satisfy some axioms. Continuous spaces like lines and circles and surfaces are topological spaces, and they give us some cool constructions with products. The product of two lines is a square. The product of a line and a circle is the side of a cylinder. If we take the product of two circles, we get a torus. Products of algebras are also algebras, products of modules are also modules, the list goes on and on. Let's try something more esoteric. A graph is a set of vertices along with a set of edges which are attached to those vertices. We'll only look at simple undirected graphs, meaning the edges don't have a direction and a vertex can't connect to itself. Can we take a product of graphs? Of course we can. Just take the Cartesian product of the sets of vertices, and then fill in the edges. Except there's multiple options for how to do that. We could add a copy of every edge to each copy of each graph in the product, or we could connect two vertices if and only if they are connected in both original graphs. Or we could do both. Okay, maybe taking a product of graphs isn't quite so obvious. But actually, this raises a question with the previous examples. When we took the product of the real numbers with itself, I claimed that the result had addition and scaling operations making it a vector space. But the Cartesian product only cares about the underlying sets. It doesn't give us those operations. That extra bit of data is something we have to manually add to the Cartesian product in order to turn it into a vector space. And then we need to verify that it satisfies the axioms of a vector space. Fortunately, it doesn't matter what vector spaces we start with. The product will always be a vector space if we give it component-wise addition and scaling. But that's a fact that needs to be proven, and different structures require different proofs. For instance, topological spaces have a very different product construction. I said the product of two lines is a square, but what are the open subsets of a square? It's not enough to just take products of subsets of the two lines, that would just give rectangular subsets. So we need to add in potentially infinite combinations of these rectangles, and then we need to prove that what we end up with is actually a topological space. With graphs, we don't even know where to start, because there's multiple things that the product could be, and none of them are particularly self-explanatory. All of these mathematical structures have Cartesian products, but their products are constructed in different ways, and for some of them it's not clear which construction is the most canonical. Wouldn't it be great if there were a way to connect all of these under one construction? Wouldn't it be amazing if there were a single, entirely rigorous definition that uniquely determined the product for any algebraic structure? But that can't be possible, right? All of these structures follow completely different rules. There's no way they could all be captured by a single definition, right? Well, what if I told you that there was a special kind of mathematical formalism which did cover all of these things? A formalism where all the products I just described are explained by the exact same framework. This formalism does exist, and it's called category theory. Now, category theory, and even products specifically, is something that other people on YouTube have already made videos about. Isomorphic made a lovely video a couple of months ago on almost exactly the same topic, but I want to give my own description, for a couple of reasons. Firstly, I want to describe category theory in a way that makes it feel inevitable, like it's the only sensible way to describe algebraic structures. Secondly, I want to go through the example of products in extremely high detail, which I think is important for a topic as logically complex as category theory. And thirdly, I started scripting this video ages ago and now I'm in too deep. The plan is this: I'm not going to outline the entirety of category theory or all of its myriad applications. Instead, I'm going to look at a very specific construction, the product, to demonstrate a very specific application, abstract algebra. And maybe along the way we'll learn something about the way we understand mathematics and logic. The key idea that is going to allow us to generalize products to arbitrary structures is that Cartesian products are really useful for describing multivariable functions. For example, consider the function which takes two real numbers and adds them together. Instead of thinking of this function as having two inputs, we could instead think of it as having one input, which is a pair of real numbers. Then the set of all possible inputs to the function is the set of all pairs of real numbers, which is exactly the Cartesian product R cross R. More generally, if f is a multivariable function defined on the sets a and b, then we can interpret f as a single variable function whose domain is the Cartesian product of a and b. You might have noticed in the introduction that I already used this notation when defining algebraic structures. For instance, the scaling operation on a vector space V is a function r cross v to v. It takes a pair of a scalar and a vector and multiplies them together. Before we go any further, let me set up some notation for single variable functions. I'm going to draw a function between two sets as an arrow. The set of inputs to the function is called the domain, and the set of outputs is called the codomain. If I have a function f from a set A to another set B, and then another function g from B to another set C, then applying g to the output of f gives a function directly from A to C. This is called function composition. Now, whenever I have a diagram like this, there might be multiple ways of getting from one set to another. We say that the diagram commutes, or is commutative, if every path between two sets composes to give the same function. Here's an example. The horizontal arrows in this diagram are functions which take a real number and double it, and the vertical arrows take a real number and triple it. Is this a commutative diagram? Well, we need there to be a single function from the top left copy of R to the bottom right copy, which is equal to both of these paths. And indeed there is. It's the function multiplying a number by 6, so this diagram commutes. On the other hand, if I replace the vertical arrows with functions that add 1 to a number, then this diagram does not commute. For example, the real number 0 gets sent to a different number depending on which path we take. Now let's go back to multivariable functions. Suppose the function f takes two inputs from the sets a and b, and its output lands in the set c. Then, as we saw before, f can be treated as a single variable function from a cross b to c. Now, let's suppose that I have two other functions, g and h, whose codomains are a and b respectively. For simplicity, I'm going to assume that g and h have the same domain. Let's call it x. I should be able to compose these functions with f by just plugging the outputs of g and h into f. But it's not obvious how to do that on the level of diagrams, because these arrows don't connect. Maybe we can get some arrows between a and b and their product, so that we can link everything up. Here's an idea. We have a function going from the product to a, which takes a pair and spits out its first entry. Similarly, we have a function going from the product to b, which takes a pair and spits out its second entry. These are called the projection functions. Okay, that didn't actually help because these arrows are going in the wrong direction, so we still can't compose anything. In order to compose these functions, we would need an arrow directly from x to a cross b. My claim is that there is exactly one such function that makes this diagram commute, and that unique function is exactly the function describing the composition of f, g, and h. Let's check this claim. For an arbitrary element little x inside big X, we need to figure out the pair which this function sends x to. There are two paths taking us from x to a, and we need to make sure that these send little x to the same element. That means this projection map must send this mystery pair to gx, which means that gx must be the first entry of this pair. There's also two paths taking us from x to b, and these must both send x to hx. That means hx must be the second entry of this pair. So there's only one option for this mystery function. It has to be the function that sends an element x to the pair gx-hx. Now notice that if we apply f to this pair, we get exactly the composition of f with g and h, and we're done. This potentially gives us an alternate way to define the product. A product of two sets A and B is another set, which we denote A cross B, along with two functions from A cross B, one with codomain A and the other codomain B, such that, for any other set X and functions G and H from X to A and B, there exists a unique function from X to A cross B, making this diagram commute. That's a real mouthful of a definition, and we haven't even verified that the Cartesian product is the only set satisfying this condition. Spoiler alert, it kind of isn't, but let's ignore those problems for the moment and get to the thing that we're trying to get to, a generalization of the product to other objects. For instance, does this definition still work for vector spaces? And more importantly, does it automatically spit out the correct vector space structure on the product? Let's suppose that A, B, C, and X are actually vector spaces, so they have addition and scaling operations. Now obviously, all the working out we did before works exactly the same. There's a unique function from X to A cross B making this diagram commute, and its composition with F describes the composition of G and H with F. But that doesn't tell us anything about what addition and scaling operations A cross B should have. How do we fix this? The answer lies in the functions. We don't just work with any functions between vector spaces, we want to work with linear functions. Linear functions respect the vector space structure, in the sense that adding two vectors and then applying the function is the same as applying the function and then adding, and similarly for scaling. Linear functions are the backbone of linear algebra, the study of vector spaces. So when we're building these diagrams, we want to make sure that all the functions we're working with are linear. So let's impose that G and H are linear. We also want f and these projection maps to be linear. Will that give us enough information to figure out the vector space structure on A cross B? Let's try. Suppose I have two pairs of vectors, A1, B1 and A2, B2. We want the addition operation on A cross B to be such that if I add these pairs together and then project to A and B, I get the same result as if I project and then add. There's only one pair in A cross B whose projections are these sums of vectors, and that's this pair, A1 plus A2, B1 plus B2. This tells us that A cross B has to have component-wise addition. I'll leave you to check that the same thing works for the scaling operation. So just by looking at the projection maps, we've concluded that there's only one possible vector space structure for A cross B. So that's great, but there's one other cool thing that we get out of this. Remember that we're trying to compose multivariable functions. We know from our understanding of the product of sets that there is a unique function from X to A cross B describing the composition of F with G and H. This unique function is also linear. This is very important because now this whole abstract definition of the product that I described for sets works exactly the same, word for word, for vector spaces. All we have to do is replace functions with linear maps, and everything follows the exact same rules. And now we finally have a template for how to generalize things. Take this definition, replace any occurrence of the word set with some other type of mathematical object, and replace any occurrence of the word function with the type of function respecting the structure of that type of object. In a huge number of cases, this will give a definition which, 1, is satisfied by the Cartesian product, 2, uniquely defines a structure of that type on the Cartesian product, and 3, for which the Cartesian product is the only object satisfying that definition, up to some kind of isomorphism. The last thing is something we still need to prove. We'll get to that. First, let me describe precisely what framework we're actually using for this whole discussion. A category is a mathematical structure consisting of three things: a collection of objects, a collection of morphisms, and a composition operation. The objects don't have any internal structure, they're just there for indexing purposes. Each morphism has two objects that it's attached to, called its domain and codomain. And the composition operation is an operation on morphisms, but it's only defined on pairs of morphisms that have the same codomain and domain respectively. So if I have a morphism from A to B and a morphism from B to C, then I should always be able to compose them to get a morphism from A to C. The composition operation only needs to satisfy two properties. Firstly, it must be associative, meaning it doesn't matter where we put brackets, and secondly, there must be an identity morphism for every single object. Composing the identity on an object with any other morphism going to or from that object leaves that morphism unchanged. Okay, let's look at an example of a category. Set is the category of sets. Its objects are all possible sets, its morphisms are all possible functions between sets, and its composition operation is composition of functions. Now, if you know a little bit of set theory, you might have some alarm bells going off. How do we describe the collection of all sets? You can't form a set of all sets, it would have to contain itself. The collections of objects and morphisms are actually a more general thing called a class, and it is possible to have a class of all sets. The trade-off is that it's not quite so straightforward to talk about things like subclasses constructively in the same manner as sets. This is a problem that we will just kind of ignore. Sets and classes behave pretty similarly for the most part. Here's some more examples of categories. Vec is the category of vector spaces. Its objects are all possible vector spaces, its morphisms are all possible linear functions, and its composition operation is, once again, composition of functions. Group is the category whose objects are groups and morphisms are group homomorphisms. Top is the category whose objects are topological spaces and morphisms are continuous maps, etc., etc. So right now, all we're doing is taking the algebraic objects we already know and collecting them into gigantic families. And now, finally, we can get to the actual definition of a product. Suppose I have two objects, A and B, in some category. If I have another object, P, a morphism from P to A, which I'm going to call PA, and a morphism from P to B, which I'm going to call PB, then that collection of three things is called a product if it is universal. Universal means that if I have another collection of these three things, an object Q and morphisms QA and QB going to A and B, then there is a unique morphism from Q to P such that the maps QA and QB factor through PA and PB via this morphism. That is to say, this diagram commutes. This is almost the same setup that we had before, I've just rephrased it slightly. An important change that I've made is to include the projection maps PA and PB into the definition, so that we don't have to specify them in advance. Now, notice that I said a product and not the product. This is because we haven't proven that the product is unique. And actually, it's not unique. Let's say I'm in the category of vector spaces, and I want to take the product of the real numbers with itself. I can immediately think of two different ways to do this. We can write a pair of real numbers as a column vector, so the vector space of 1 by 2 matrices is a product. But we can also write a pair of real numbers as a row vector, so the vector space of 2 by 1 matrices is also a product. Okay, you might be thinking, Joe, these are obviously the same thing. What's the problem? But they're not the same thing. Let me give some more examples. The set of complex numbers is also a two-dimensional real vector space. The set of functions from the set 0, 1 to the real numbers is a two-dimensional vector space, with pointwise addition and scaling. The set of functions from any two-element set to the set of real numbers is a two-dimensional vector space. The set of real polynomials of degree at most 1 is a two-dimensional vector space. These all have the same structure. They're all two-dimensional vector spaces, but they don't have the same underlying sets. Sure, there's maps between all of these, but there's also infinitely many maps, and it's not clear which we should pick. Moreover, each of these examples has many projection maps we could choose. You could say that the collection of all two-dimensional vector spaces is infinite, but that's an understatement. The collection of all two-dimensional vector spaces is so ill-defined that it doesn't even form a set. It's a class, and all of the things in that class, along with appropriate projection maps, could be a product of the real numbers with itself. So we don't want to show that the product is unique. Instead, we want to show that it's unique up to isomorphism. The categorical definition of an isomorphism between two objects x and y is a morphism from x to y which has a two-sided inverse. That is, a morphism from y to x, such that if we compose these two morphisms in one direction, we get the identity morphism on x, and if we compose them in the other direction, we get the identity morphism on y. If two objects have an isomorphism between them, then we say that they are isomorphic. Now, in most of the examples we've looked at, an isomorphism is just a bijective function, a function which sends every element of x to every element of y with no overlaps. This means that two sets are isomorphic if they have the same cardinality, the same number of elements, and two vector spaces are isomorphic if they have the same dimension. There's a little bit of an oddity with isomorphisms in the category of topological spaces, but we'll get back to that later. Let's see if we can show that the product is unique up to isomorphism. Suppose P and Q are two different products of A and B, so they each have their own projection maps. Since P is a product, by the definition of the product, there is a unique morphism from Q to P, let's call it F, making this diagram commute. But Q is also a product. Hang on, let me draw another copy of P so we don't have overlapping arrows. Since Q is a product, there is a unique morphism from P to Q, let's call it G, making this diagram commute. Now, composing these two morphisms gives a morphism from P to P, and if we now remove the Q in the middle, we get a commutative diagram that looks like this. This also looks like a product diagram, and now we use the one detail of the definition which we haven't used yet. This morphism, making this diagram commute, must be unique. There is only one morphism satisfying this property. But the identity morphism on P certainly makes this diagram commute, and since it's the only morphism with that property, FG must be equal to the identity. Now we just need to show that GF is the identity morphism on Q, and that can be done in exactly the same way by reversing P and Q. That means F and G are inverses of each other, and we have an isomorphism between P and Q, and moreover, this isomorphism commutes with the projection maps. So the product of A and B is unique up to isomorphism. Now, the amazing thing about this proof is that it didn't make any assumption about what category we're working in. We didn't even consider the elements of A and B, and we didn't even require that they have underlying sets at all. All we needed was relationships between morphisms. Which means not only have we shown that the product of sets is unique, and the product of vector spaces is unique, we've shown that any product in any category is unique up to isomorphism. In fact, we have an even stronger result. The product is unique up to a unique isomorphism. By the definition of the product, these maps F and G that we used in the proof are the only maps commuting with the projection maps on P and Q, so there's only one canonical way to identify these two products. For example, we saw earlier that the space of two-dimensional row vectors and the space of two-dimensional column vectors were both products of the real numbers of itself. If we take the projection morphisms to be the functions extracting the first and second entries of a vector, then there is exactly one map between these two vector spaces respecting that product structure, and it's the map sending a column vector of components AB to the row vector of components AB. And this isn't the only thing that we can prove about products. There's two obvious ways I could take a product of three objects. I could take the product of the first two, and then the product of the result with the third, or I could product the last two and then product the result with the first. Actually, there's another thing we could do. A product of three objects, A, B, and C, is another object along with morphisms to A, B, and C, which is universal, meaning that any other object with its own morphisms to A, B, and C factors through the product. All of these definitions turn out to be the same, in the sense that there are unique isomorphisms going between them. I'll leave you to prove this as an exercise if you want. There are also other ways in which the product describes multivariable functions. If I have two pairs of sets, a, b, and x, y, and two functions, f from a to x and g from b to y, then I can construct a function from a cross b to x cross y which sends a pair ab to fagb. How is this function described from the category perspective? Well, let's draw a diagram. If we compose the projection maps on A cross B with the functions f and g, we get morphisms from A cross B to each of x and y. So the definition of the product kicks in and gives us a unique morphism from A cross B to x cross y, making this diagram commute. This morphism is exactly the product of f and g, like we expected. The point I'm trying to make here is that category theory gives us a language to understand why the product is interesting, what properties it has, and what it means to say that the Cartesian product is the unique object with those properties. When we take the Cartesian product of two groups, for instance, there might be many ways of giving it a group structure, but there's only one way to give it a structure with all the properties of a product. I mentioned that there's several intuitive ways to take a product of two graphs, and it's not clear which one we should choose. However, we can form a category of graphs, the objects are undirected simple graphs, and the morphisms are functions on the graph sets of vertices, such that if two vertices are connected by an edge in the domain graph, then their images are connected by an edge in the codomain. In this category, it turns out that this graph is the categorical product, the one which has an edge whenever there's a corresponding edge in both graphs. Checking this is another exercise. Maybe this weird construction of a graph product wasn't interesting before, but it is interesting now. It's the universal graph for describing two variable functions on these two graphs. But actually, this depends on how we choose our morphisms. If we allow a graph morphism to send two vertices connected by an edge to the same vertex, then that adds a bunch of morphisms to our category, and the product changes. It's now this graph, which includes edges between vertices that have one component the same. So there's a correspondence between what morphisms you want and how the product behaves. Previously, we had to come up with special rules for the product on each type of mathematical structure, but now we have a single definition which automatically prescribes what the product structure should be in all of those cases. There's just one problem. This definition is not constructive. We know that a product is always unique, but we don't always have a simple recipe that allows us to write down what the product is. We also don't have a simple recipe to prove that a certain object is a product. Groups, graphs, vector spaces, and topological spaces all need to satisfy different properties, and we need to individually check those properties to make sure that the product actually exists. This is an unavoidable problem. The more broad and all-encompassing a theory of mathematics is, the less it says about the specific topics it encompasses. Category theory is extremely broad and can connect a lot of mathematical objects in truly amazing ways. But if you want to actually prove anything about those objects, then you often have to delve into the theory behind those individual objects themselves. It's also possible to find categories where products don't exist. One example is the category of fields. A field is a set with two operations, addition and multiplication, which are associative, commutative, and have identities which we denote 0 and 1 respectively. Every element must have an additive inverse, and every element except 0 must have a multiplicative inverse. Some examples are the real numbers, the rational numbers, and the complex numbers. A morphism in the category of fields is a function which commutes with both addition and multiplication, and sends 0 and 1 in the domain to 0 and 1 in the codomain. These functions have a peculiar property. They are always injective, meaning that they send non-equal elements of the domain to non-equal elements in the codomain. There's another exercise for you. So let's suppose that f is a field and try constructing the product of f with itself in the category of fields. We need a field P with two projection morphisms to f. Now let's consider another field Q which also has two morphisms to f. We need there to be a unique morphism from Q to P, making this diagram commute. But Q can be anything, so what if we take Q to be f, and these morphisms to be the identity morphisms? Then we get identity morphisms going back the other way. Now, in any other category, this diagram would not necessarily be commutative. If we pick an element of f and chase it around the diagram, it does end up back at the same element of f. But the same thing doesn't work for p. If I take an element of p and chase it around the circle, it can end up at a different element, as long as this new element gets sent to the same element of f. But in the category of fields, this morphism is injective, because every morphism is injective. So it's not possible for two distinct elements to have the same image under this projection. So the only possibility is that P is isomorphic to F. That's very strange, because this is an example of a product whose underlying set is not the Cartesian product of sets. And there are some fields for which this does actually work. The field of rational numbers, for example, has a product with itself, and the product is again the field of rational numbers. But it doesn't work for every field. If I take F to be the field of complex numbers, C, then there are some non-trivial field homomorphisms from C to itself. Specifically, there's a homomorphism sending the imaginary number I to negative I. Using these unusual maps, we can quickly show that the product can't exist. There's no projection maps which will commute with every possible choice of morphisms. So, there are categories where some products are not Cartesian products on the underlying sets, and there are categories where some products don't exist. But that's to be expected. As I said, category theory is extremely broad, and covers some very strange cases. But this doesn't have to be a bad thing. Some of those strange cases can be fascinating. Remember that the only piece of information in a category is the composition map. Objects and morphisms don't need to have any internal structure. I'm going to define a category which I'll call int. The objects in this category are integers, as in whole numbers. There will be exactly one morphism going from an integer x to an integer y whenever x is less than or equal to y, and the composition is defined such that if x is less than or equal to y, and y is less than or equal to z, then the composition of the morphisms from x to y and y to z is the unique morphism from x to z. Int is a perfectly valid category. The objects have no underlying sets, the morphisms have no underlying functions, the composition operation is definitely not function composition, but it is still a category. Do products exist in this category? If I have two numbers, x and y, their product is a number with morphisms to both x and y, meaning it must be less than or equal to x and y. We also require that any other number less than or equal to x and y must have a morphism to the product. So, the product of x and y is the biggest number that's less than or equal to both x and y, which means it's the minimum of x and y. How cool is that? Now, two numbers always have a minimum, but they also have a maximum, which raises a question. Is there some kind of opposite construction to the product, which on this category gives the maximum of two numbers? And if there is, what does it look like on other categories like set and vec? This dual construction does exist, and it's called the coproduct. To define the coproduct, we just need to take the definition of the product and flip all the morphisms. A coproduct of two objects A and B is another object C along with morphisms IA and IB, this time going from A and B to C, which is universal. That means that if there is another object D with its own morphisms from A and B, then those morphisms factor through IA and IB via a unique morphism from C to D. Just like with the product, you can prove that the coproduct is unique up to unique isomorphism. These special morphisms IA and IB are called the inclusion morphisms, which is why we're denoting them with the letter I. Now, in this weird category int that we constructed before, the coproduct of two integers is just their maximum. But what is the coproduct in the category of sets? Well, if we need functions going from A and B to the coproduct, then one possible candidate is the disjoint union, which is the set of all elements in either A or B with no overlaps. The usual union is denoted with a cup symbol, so for the disjoint union I'll use this angular cup. Is the disjoint union, along with the inclusion functions on A and B, a coproduct? Let's check. If I have another set D with functions coming from A and B, I want there to be a unique function from the union of A and B to D commuting with these functions. But of course there is. A function on the union of A and B is just a pair of functions on A and B individually. So in the category of sets, all coproducts exist and are given by the disjoint union. What about vector spaces? Is the coproduct still the disjoint union in the category of vector spaces? Well, that wouldn't make sense because there isn't an obvious way to give a union of vector spaces the structure of a vector space. For example, there would be two different zero vectors. But the zero vector gives us a hint at how to find the coproduct. You see, all the way back when I was defining the projection maps on sets, you might have wondered why I chose to find a function from A cross B to A, but didn't bother trying to find a function going the other way. The problem is that even though there are functions going from A to A cross B, none of them are canonical in any sense. We would want to send an element A to a pair whose first entry is A, but what about the second entry? There's no canonical element of B we should choose. But now, in the world of vector spaces, there is a canonical choice, the zero vector. If A and B are vector spaces, then the function from A to A cross B sending a vector A to the pair A0 is a linear map. Doing the same thing for B, we get a possible candidate for the coproduct. We just need to check that it's universal. Let's say that there's another vector space D with maps G and H going from A and B to D. A function from A cross B to D, making this diagram commute, must send A0 to GA and 0B to HB. But this function must also be linear, so we can sum these to show that AB must be sent to GA plus HB. That means this function is the unique possible function and universality holds. So in vec, all products and coproducts exist, and they are the same. What about the category of groups? Groups have some similarities with vector spaces, and we've seen that they handle products in basically the same way, take the Cartesian product with component-wise operations. So if A and B are groups, then a candidate for their coproduct is to take the Cartesian product with the inclusion maps pairing elements of A with the identity of B, which I'll denote 1B, and pairing elements of B with the identity of A, which I'll denote 1A. But while this worked for vector spaces, it doesn't work for groups. If I multiply the pair A1 with the pair 1B, I get AB, which is the same as if I multiply them in the order 1B then A1. It might be possible that there's some bigger group, containing both A and B, in which the order does matter. And if such a group exists, then A cross B can't be the coproduct because it doesn't have a universal map to this group. The actual coproduct is something called the free group on A and B, and it's the set of all alternating sequences of elements of A and B. So, confusingly, the coproduct of two finite groups is typically an infinite group. So, unlike products, coproducts look completely different in set, vec, and group. But there is a way to connect them. All of these coproducts are some kind of completion of a disjoint union. In vec, the coproduct is found by taking the union of two vector spaces, joining them at their zero elements, and then adding in linear combinations of elements to get a complete vector space. Similarly, in group, the coproduct is found by taking the union of two groups, joining them at their identity elements, and then adding in elements by multiplying them with no extra relations to get a complete group. Still, maybe coproducts don't feel as natural as products, and that's okay. Rigor is more important than intuition. I mentioned earlier that in almost all the categories we've looked at, an isomorphism is the same as a bijection, a one-to-one map. But we haven't yet talked about top, the category of topological spaces, where the morphisms are continuous functions. A continuous function just needs to send nearby points in the domain to nearby points in the codomain. For example, if I have a line that's closed at one end and open at the other, then I have a function from that line to a circle, which just wraps it around the circle. This function is bijective, so it has an inverse. But the inverse sends 2 points on either side of this connection point to opposite ends of the line. That means it's not continuous, and not a morphism in top. So this function is a bijection, but doesn't have an inverse, so it's not an isomorphism. A lot of mathematics involves taking an intuitive idea, formalizing it, and then realizing that the formalization leads to results that are completely rigorous but counterintuitive. That's why the rigor is important. If you've followed along so far, then great job, you've done a lot of heavy thinking. This is the part of the video where I'm going to start skipping over details and just rapid fire a bunch of weird category facts. I've used the word universal a couple of times to describe the product, and that's because universal constructions are much more general. We say that an object along with a collection of morphisms is universal with a certain property if every object and collection of morphisms with the same property factors uniquely through that object. For example, let's suppose that we have morphisms from A and B to another object C. Now consider an object P with morphisms to A and B, similarly to the product, but with the extra constraint that the four morphisms we end up with form a commutative square. We can then look for the universal object satisfying this property, meaning that if there is another object with morphisms to A and B making this square commute, then there is a unique map from that object to P commuting with everything. This is a different kind of universal object to the product, and it's called a pullback. If we're in the category of sets, and A and B are subsets of C, then the pullback is their intersection. Neat. There's also a dual construction you get by flipping all the morphisms, which is naturally called a pushout. If a universal construction has morphisms going out of the universal object, then we call it a limit, and if the morphisms go into the universal object, then we call it a colimit. So products and pullbacks are limits, while coproducts and pushouts are colimits. Limits and colimits are some of the most important components of category theory, and they have all sorts of fun names: kernels and co-kernels, equalizers and co-equalizers, the list goes on. Now, I didn't really give an answer to why set, vec, and group have the same products but different coproducts. I mean, I've shown how to prove it, but what's the intuition? Why are coproducts so badly behaved? Well, firstly, we need to connect these categories somehow. We can do this using a functor, which is a function between two categories that sends objects to objects and morphisms to morphisms in a way that respects composition. For example, there is a functor from vec to set, sending a vector space to its underlying set and a linear map to its underlying function. It turns out that forgetful functors like the one from vec to set tend to preserve limits, so this functor sends products in vec to products in set. This is related to the fact that they have something called a left adjoint, which is a functor going in the opposite direction which satisfies certain useful properties. This left adjoint is almost always some kind of free construction. For example, the left adjoint to the forgetful functor on vec is the functor that takes a set and builds a vector space with the given set as a basis. Some categories have a more similar coproduct to the category of sets. For example, the coproduct in top, the category of topological spaces, is just the disjoint union, since the forgetful functor from top to set preserves both limits and colimits. This is because it has both a left adjoint, the functor equipping a set with the discrete topology where every subset is open, and a right adjoint, the functor equipping a set with the indiscrete topology where the only open subsets are the whole set and the empty set. Weird. A similar thing happens in the category of graphs, where you have a functor sending a set to the graph with no edges, and another functor sending a set to the graph with all edges. Although, note that the latter is only a functor if you allow morphisms to send a pair of vertices with an edge to a single vertex. You know, these three graph products actually have names: the Cartesian product, the tensor product, and the strong product. Now, I couldn't find a way to choose the morphisms in the category of graphs so that the Cartesian one is the categorical product, annoyingly. But if you convert a graph into a category where the objects are the vertices and the morphisms are the paths in the graph, then the Cartesian product of graphs is something called a funny tensor product, as opposed to this tensor product, which is very serious. Hey, a Cartesian product of sets is just a set, and we found a way to generalize it. A group is also just a set with some extra structure. Can we generalize that? Sure we can. A group consists of a set G and three functions. The first is a function from G cross G to G describing the group multiplication, the second is a function from a one-element set to G describing the location of the group identity, and the third is a function from G to itself, sending an element to its inverse. Now take the axioms of the group, associativity and the properties of the identity and inverses, and then turn them into commutative diagrams, and voila, we've got a categorical definition of a group. Why is this useful? Well, now that our definition has no mention of the elements of G, we can take the whole thing and transport it to another category, as long as that category has products and something which behaves like a one-element set, called a terminal object. So a group is just a group object in the category of sets. But what's a group object in the category of topological spaces? It's something called a topological group, a group where the operation is a continuous map. There's plenty of great examples of these, for instance groups of invertible matrices. A special case of this is Lie groups, which are group objects in the category of differential manifolds. What's a group object in the category of vector spaces? It's, just a vector space. It turns out the group operation just ends up being vector addition. What's a group object in the category of groups? It's just a group, right? No, you drongo, it's an abelian group. Get your act together. This actually ties into why group and vec have similar products to set. Groups and vector spaces are defined pretty much entirely with morphisms between products. Fields, on the other hand, have this weird condition that every element except 0 be invertible. That means the function sending an element to its inverse is a function on the subset of non-zero elements of the field, not a function on the whole field, and that makes it a lot harder to find a categorical definition for. I've heard that this makes fields annoyingly fiddly to formalize in proof-of-system programs like Lean. So, you know, functors between categories. Those are kind of like morphisms of categories, right? Can we form the category of categories? We absolutely can, it's called cat. But really we should be thinking of this as a two category, which is a special kind of category that has two different kinds of morphisms. This is because functors themselves have morphisms between them called natural transformations. For example, remember when we had a morphism f from a to x and g from b to y, and combined them to form a product morphism from a cross b to x cross y? Well, we can view taking a product with a to be a functor, and taking a product with x to be a different functor, and then taking a product with f is a natural transformation of those functors. Actually, we don't have to fix the objects a and x. The product on a category C, if we can specify it, is a functor from C cross C to C. What's C cross C? It's the product in the category of categories, of course. I want to emphasize that this video is not an overview of all of the things category theory is useful for. While it originally spawned from abstract algebra, category theory has gone on to become an important tool for mathematical logic, which in turn led to applications in functional programming, among other things. I just happen to know more about the algebra side of things, because that's what I study. There's a book by Eugenia Cheng called The Joy of Abstraction, which essentially argues to non-mathematicians that abstract category theory is enjoyable to study on its own merits, and potentially is a superior framework for understanding everyday life. It's a convincing argument, but I don't want to go quite so far down that rabbit hole. I generally assume that anyone willing to watch an hour-long video on category theory already trusts that I have something interesting to say. But in the context of mathematics itself, I do think that category theory, along with topics like set theory, mathematical logic, and proof structure, is something that should be taught earlier in higher education. It's hard to justify category theory on its explicit value, much in the same way that it's hard to justify set theory, but the implicit value of category theory, as a language to express concepts that are shared in almost every area of mathematics, is unparalleled. By the way, I've heard from multiple sources that Australia has played a big role in advancing category theory, especially higher category theory, which looks at even more generalizations beyond two categories. As an Australian myself, I can confirm this, but also, it's specifically Macquarie University. Like, sure, Australia is chockers with category-pilled unis, but Macquarie University is the real deal. I don't know why Macquarie became such a central hub for category theory, but whatever the case, on behalf of Australia, I apologise that everyone now has to deal with phrases like free, strict, N category on the terminal globular set, alongside all the incomprehensible slang our country has already produced.